call it the holy grail, but I think humanity is going to be working on fusion for the rest of humanity.
Ahmed, it's great to have you here. Appreciate you taking the time to come on the podcast. We're sitting here today at the PPPL, the Princeton Plasma Physics Laboratory in New Jersey. It's great to be here. Beautiful weather, as we can see, with some the forest behind us. Thanks for coming on.
Thanks, Alex, for having me on this podcast. Yeah, it's the first time I'm getting a podcast, so I'm excited.
Yeah, amazing. And we're going to talk a bit today about advanced fuels. And I know that's an area that you've been exposed to throughout your career and done some work on it. I'm very excited to hear more about the new recipes that are kind of emerging when it comes to fusion.
I'm a scientist at Princeton Plasma Physics Lab. I'm also a program director at ARPA-E, which is the Agency for Advanced Research, part of the Department of Energy. But to give you a little bit of background how I got into the field, basically, this is a little bit of I grew up, from Burkina Faso. It's a country in West Africa. And I moved to the US to just do my undergrad, to finish my undergrad. So I was mostly a math and physics major. And the thing that was interesting is I get the undergrad, the first year, there's what's called, you may not know, it's called a research experience for undergraduates, right? Basically, the summer, you go do research at the facility. So I was offered this position at Princeton Plasma Physics Lab back in '98 to come here and do research. So that was the first exposure to plasma per se for me and research. So I work with two scientists at Princeton from the theory department. And I thought it was a great experience because they exposed me to research in general, which I had never had before. I was a junior by then, so in college. And then I was like, all right, plasma is really cool. You get plasma as part of the sun, and then you can get energy out of it. My thought was like, man, this is great. Wow, what are we waiting for? You take water, seawater, and then you get plasma. I mean, the way to sell it, right? So I got excited about it. But instead of diving into fusion directly, which is what I basically started going back to, I did my PhD into basic plasma. Basic plasma, just understanding the fundamentals of plasma. And then it's very low temperature. So it's not a fusion grade. It's just like what you get in space and so forth. And then after my PhD, I decided to get closer. So it was basically a cylinder of plasma, like a linear device, right? Simple, easy to diagnose, you probe. And then the next thing I'm like, okay, let me do something where I wrap the cylinder into a donut, but not do a tokamak yet, but just like a simple magnetized tokamak, torus they call it. And then I spent 2 years in Switzerland where I did that. And I quickly saw the complexity because, if something that's linear, it's easy to measure somewhere. When it bends, then you have the curvature, it becomes a bit of a mess, but also something challenging in terms of you have to come up with clever ways to probe the plasma. And then after 2 years, I decided to uproot the family and then go to Australia. And that was a bit of it's an interesting story because I just read a paper from a scientist there, John Howard. It was great. And I read the paper. I was like, I want to learn this technique just like that. And I pinged him, and turns out he had just won a grant from the Australian research grants as like the equivalent and the National Science Foundation type. And then he said, you got a job. Here's a CV if you want to come. And I'm like, I was taken aback, no interview, just come in. Never been to Australia. Look at me, and I'm like, sure. And I pack up, I go on my bike, because I went first, and then my family joined after that. Spent about 1.5 years where we worked another tokamak, and that's where I started really getting exposed in tokamak. And that was the best experience because I realized I saw the complexity, the interest, and what fusion can do, and I started learning fusion from there. And then after 2 years, I moved to the US at Princeton Plasma Physics Lab. And ever since, I've been involved in fusion devices and trying to improve the performance, from the basic phenomena to all the way to fusion-grade plasma. So in the meantime, I worked on most tokamak abroad, actually, because NSTX had to go to an upgrade phase, and I had to find something to do in the meantime. So that's kind of my journey, and I've been since hooked on fusion because I feel like this is, people call it the holy grail, but I think humanity is going to be working on fusion for the rest of humanity, period. It's like, I see it that way. There's no better source of energy than fusion, effectively. But right now we're tinkering about other technologies, but I feel like fusion is what we want to be at. And then now you speak about fusion in general. So in the meantime, I started a job at the Department of Energy called Advanced in the meantime, and it was a fusion program director. And it allowed me to really go to higher level and understanding all the energy technology out there. And then I started doing a more deep dive in fusion and everything that has to do with other concepts, which actually was the best thing I think in my career, was like to learn other concept, but not coming from your own concept, but your role is to kind of understand what's in the landscape. And then we funded fusion startup, funded also fusion project, but in fusion, I always think about deuterium and tritium for a primer. This is like the essential fuel you need in fusion, right? This is what people are going to be doing just because it's easier compared to other fuels. And let me back out a little bit. I mean, the thing that's interesting about fusion is like any kind of heating source, basically. You have a furnace, basically, and you need a fuel. Mm-hmm. And then fuel, the DT is a really easy one. Everyone's going to start with fuel for DT fuel. But there's also what's called advanced fuel, non-conventional, non-mainstream, right? Although there are a few companies looking at that. Yeah. And they have their own advantages. So for the general audience, the thing that you want to think about is deuterium and tritium gives you a neutron that comes out, and an alpha particle is charged particle, which is helium-4. But a neutron coming out has 80% of energy, and to get fusion with deuterium and tritium, it's relatively easy compared to other advanced fuel. And then so the world is going to work on this. Now, what I'm saying, fusion 2.0 might come down to something less harsher. What I mean by harsh, the neutron comes and hits your wall, which is your fireplace, effectively, yes. And then damages. You have to find the right material. It could be challenging, but I think the humanity is going to say, well, this is too complex. Yeah. And then also you have to deal with tritium. You have to breed it and all that. So this is complex. Let's go to something simpler. And then you go, okay, what does simply mean? Something that doesn't have neutron, for example, that produces a charged particle. And you can think of a system where, for example, you have a charged particle coming out. Instead of spinning a turbine by boiling water, first you just get a charged particle and you put a electron in the grid. Yeah. Okay. So why not? I mean, you ask yourself, why not? And then you realize, okay. Then you go back and physically realize, well, we're not doing this because it requires 10 times more heat to get to these fusion conditions. Uh-huh. And by doing so we're saying this is a little too challenging. We don't have the means to heat it. And then there's all the other radiation mechanisms that basically leaks out the heat. So you can really never achieve this fusion. So the main fusion fuel that people are aware of is deuterium and helium, helium-3. Helium-3 is really known as something that people want to mine from the moon. There's also proton boron. This is abundant. Proton and boron are abundant. And these two fuels, for example, can fuse. For example, deuterium and helium will give you a neutronic byproduct, mostly charged particle. Proton boron will give you 3 alpha particle with charged particle that comes out. Yeah. But the energy that you get per fusion reaction is smaller than deuterium and tritium. Okay. But you have all the great advantage that is that, okay, I don't need to worry about the vessel to be like that should be neutron resistant. You can get the charged particle coming out straight out, put an electron in the grid. I'm making things a little simpler right now. Yeah. Okay. But the challenge is really the physics. Yeah. The physics. So there's a school of thought right now that said, listen, deuterium and tritium, the challenge is engineering. Yeah. Putting all these pieces together, it's very complicated. Or we can go back to the physics, work hard at the physics, nail it, get it right, then the engineering become easier. Yeah, so understood. There's 2 paths. So basically you're like, okay, this is interesting. So the second school of thought is pushing for the advanced fuel. And I do believe that advanced fuel is something we'll be doing in the future. Yeah. And I want to throw one thing in advanced fuel. You can think about also, I don't know if you spin polarize those fuels, that's also an advanced fuel because basically it's a higher grade fuel that gives you more yield and fusion power. So these are things you want to think about. The biggest challenge for one of the advanced fuel for deuterium and helium-3 is getting helium-3. Okay. That's not readily available, at least at a quantity. And especially now, if you think about it, it's we have quantum computing that is that's picking up. And quantum computing is also requiring helium-3. So we need enough supply to be able to get burning plasma with the helium-3. But fortunately, if we can get, there's another reaction called deuterium-deuterium that could produce, there are two branches. One of the branch can produce tritium, which could be interesting. Imagine, you can imagine someone say, listen, I don't want to produce power. I just want to produce tritium, and I'll wait 12 and a half years, 12-year roughly half-life, and then it decays to helium. I sell it.
Sure.
So you're going to have this supply down 12-year cycle. Or you can say, forget about all this thing, go to Jupiter or the moon and mine it.
Yeah. So let's I want to unpack and go through a few of those elements, because there was like an amazing amount of information. That's really good. So I think, so advanced fuels are basically, this class of fuels that are steer away from the original recipe of deuterium and tritium.
Right.
And deuterium and tritium, the physics and science are fairly well understood in comparison relatively to these other fuels. Right. But basically the lot of energy from the neutrons are just missiles through materials and create a lot of engineering and operational challenges.
Absolutely.
So basically this new class of fuels has kind of a variety of benefits. Some of them being that they have charged particles that don't require a thermal cycle to deliver and won't have the same kind of materials challenges. But what they do have kind of some deep physics and scientific uncertainties questions that need to be answered. Yeah. So and we'll go into some kind of more of those. I think we'll go deeper into some of those challenges afterwards, but thinking about those benefits you spoke about. Right. So when you're saying, there's charged particles, so what we're basically saying is we're going to transcend what is currently thermal generation steam cycles.
Correct.
So what kind of efficiencies or benefits does that mean from like a power plant level?
So that's a good question. I mean, there have been work being done, but from a power point of view, if you can go above the 40% thermal cycle that you get, efficiency thermal cycle that you get, typically, you can, for charged particle, with a little bit more work, one can achieve about 70%. Yeah. Right. Which would be a game changer, right? I do believe that the thermal cycle, we're capped, unless you go to very high temperature exhaust coming in, you're capped 30, up to maybe 60% with supercritical CO2, which is something that people are working on. So I feel like you will gain in efficiency, and then we get better and better because we know they're charged particle. Yeah. And the beauty with charged particle, you can confine them with magnetic field, electric field. So we'll grow in getting better at confining these charged particle and push the efficiency as close to 90, 95%. And that's where the challenge is going to come, to just get this every 1% out of there. So I do believe that there's a chance, but we need the full analysis done. Yeah. And it hasn't been done because one of the challenges you would have also is radiation. Yeah. Because you need about 10 times more heat to get the fusion condition, 10 to all the way to 100 times more in NT tau, which is the fusion metric. But by going there, what happened? You heat the electron; they tend to radiate the heat out. So we'll need to figure out a way to capture this heat. So there's another approach, which is let's do energy recovery. So everything that radiates out, let's capture that energy out. So just think of, in a fusion reactor, you have radiation coming out, and then you say, all right, you come up with this material, a special material that basically is like a photovoltaic, right? Yeah. That capture this heat up with efficiency, let's say 30, 40%, even 30, 40%, it doesn't matter. You take that heat, instead of wasting that heat, you take that and then you reduce this, it increases your overall efficiency. Yeah. So that's another angle that people are doing, people are thinking about it. And usually this energy recovery approach is only thought of in the case mostly of charged particle output. Yeah, right.
Understood. So when you're saying it's kind of like a photovoltaic, that's the heat capture part. Yeah. With regards to actually capturing the charged particles, what does the mechanism actually look like? Is it kind of like how a piston works, where it's kind of changing magnetic fields?
So no, basically the charged particles are coming all over the map, right? So if you have a magnetic field that follow the field line, what you could do, you could put plate, and then the charged particle will hit a plate, and the plate will create a voltage, and you take the voltage out of that. So that's something that you would have to do, and you need to do multiple of those because the charged particle come with a certain distribution of velocities. So you need to have like plate that can capture as all velocity.
I see.
Hence the improvement in efficiency if you know how to do that. So that means you have to selectively decelerate some charge and then capture them, or let them go at the right speed and capture them. So that's why you're never going to get 100% efficiency. You always cap.
Yep, understood. So are there any nuances to, you mentioned the deuterium helium-3, you mentioned proton boron. Is there any nuances with how, how that would be installed into a power plant?
So there's slight nuances. Actually, this is interesting because deuterium helium-3, although it doesn't produce the first reaction, does not produce neutron, there is what's called side reaction.
Sure.
Deuterium, because you produce deuterium out there, you can have deuterium because you need high temperature. Deuterium will also interact in a gas of deuterium helium. So you might have tritium. And a tritium, because you are already much higher, the tritium and deuterium will interact, but a much lower quantity.
Sure.
Right? So I would say proton boron 11, in terms of fuel abundance, is the one that's really easy, and it's more likely to have to be 99% aneutronic, no neutron. So there is a little bit of ranking between the two. But what's good, and then I like the fact that it's abundant, so you don't have to go find it, but you need to figure out, because it's about 100 times, so I get 1 billion, you need to heat at 1 billion degrees Celsius, so which is like
1 billion.
Yeah, which is 10 times more.
A lot of zeros.
Yeah, a lot of zero. And the anti-tau is about 100 times more than deuterium tritium.
Okay.
So you really need to get high up there.
Yeah.
But I think it forces the community to think about means to heat it from the physics point of view.
Sure.
Which is, people have been doing that. I've been talking about it. And I think there's a company on Australia that is trying proton boron 11 using laser approach. So these are stuff with more money injected. I think once we crack the DT, I think people will start realizing that could be a good approach. And I would say that people that may be interested in that could be, for example, propulsion, things that where you want compact system with less neutron radiation.
Okay. Yeah, we'll come back to applications later, because I think that's a really interesting space. So, we spoke about kind of those benefits that in a design of a fusion power plant, there's potential efficiency gains if you don't have to go through a thermal cycle.
Sure.
And there are also there are also potential advantages associated with with supply chains because of abundance. So proton boron readily abundant, but has physics challenges that it needs to overcome. So it's kind of a tug of war there between the two. And you mentioned that deuterium helium-3. There's extraterrestrial kind of sources. You can get it from the decay of tritium.
Correct.
You were talking about you can use DD to kind of breed that. Can you talk just through that mechanism again?
So let me deuterium and deuterium has two parallel branches. One that produces tritium and proton, another produces helium-4 and a neutron. And a neutron is basically the fission type neutron is like not as energetic as a deuterium. So as a deuterium tritium, so it's 2.45 MeV. So you could, for example, and this is something that I've been working with a colleague about, you could, if we can bias the reaction and choose only one branch, for instance, to get tritium and proton, then what you can get tritium by fusing the two deuterium and a proton. So you can extract energy out of a little bit of energy just to be able to self-sustain the reaction. Yeah. You don't need to put it in a grid. Self-sustain, and then you extract a tritium. Yeah. And then you collect the tritium, and then you basically leave it to decay for about 12 years. So that's an approach to produce a tritium. It's not the only approach. And actually there are like thought, and there's like people working on ways to be able to bias the two reactions. Instead of going 50-50 above, you do like 91, 90 to 10 for instance, and then you can really push tritium production. And I can imagine a supply chain company coming in and say, listen, my goal is to sell tritium because I have two potential market. Fusion that's going to be ramping up the need for tritium. For example, the tritium supply in the US is known to be a 40 kilogram. If we want to meet some of the goal that's like that's like 375 terawatt hour in 2050s, you need to kind of ramp the number of fusion power plant dramatically, which would deplete your tritium supply in the world. So we need to figure out a way to kind of produce tritium, so the power plant, before they start breeding their own, they have sufficient tritium to be able to start a power plant. So yes, I do think that it'll be an interesting venture to look at producing tritium, and it has like application for fusion, but also helium-3 decay. So you can sell it to the quantum computing world.
Interesting. So basically, you're saying that DD fusion is a potential production mechanism for tritium.
Correct.
Interesting. So I think that so from the benefits we spoke about, obviously potential aneutronic, and the fact that you can also avoid a thermal cycle. Supply chain advantages. Are there any other key benefits that are noteworthy for advanced fuels?
I think compactness. Because you don't have to worry about radiation shielding as much as the other ones. So I would say those are the main. You can have like compact system. For DT is very, very unlikely because you need all the shielding. So I would say compactness, and so then you can use it for remote area and then just drop in a site. That's one of the main advantages.
Understood. So we spoke about the benefits, and I think it's good to explore some of the challenges. So you spoke about, 1 billion degrees. You spoke about some really hard physics regimes that need to be overcome. Let's look at DHE3 first and explore that, and then we can talk about proton boron. So tell me about what's challenging about doing this kind of fusion.
So that fusion, you need helium-3, you need about 600 million degree roughly. And just to give you a little bit of comparison, like DT is about 150 million degree to get the fuse. So 600 million degree, it is pretty challenging. So what you would need is to be able to heat at the temperature we've never seen before. Usually where we heat is with RF waves or radio frequency waves or beams, which is like charged particles. So you need to accelerate that at much higher energy to be able to heat the plasma. One can think about this in laser fusion interaction, which is potentially where you can do it because they can get very high temperature. So I would say that is the biggest challenge. And if you think about it, the metric for dihelium-3 goes an order of magnitude relative to DT. So we need ways to heat it. But once you heat it, because you typically when you heat as a plasma, you heat electron, you heat ion, because all you care is the ion to fuse, right? So, but in the meantime, what happened? You heat the electron. Electron, when I heat it, there's the radiation called bremsstrahlung that basically leaks the temperature out. So you need to find a mechanism to avoid heating the electron by heating the ion only, right? Which some physics people are coming up with clever ways to do that separately, and it becomes non-thermal, they call it. So that's the biggest challenge, and that requires more physics, small-scale tests to see if that has legs to stand on as you extrapolate. Now, once you have that, what you need to figure out is you will produce, like I said, the side reaction, right? And one of the challenges of side reaction, like I said, is DD, because dihelium-3, you need a much higher temperature than DD. So the DD in your plasma, if you heat the whole thing, will also end up fusing. And like I said, one of the branches produces tritium, and then determine tritium will start interacting. So what you would need to do is like, okay, if I want to make it purely aneutronic, let me extract the tritium as it's being produced. And then keep the charged particle. So tritium get produced in a plasma. Once you figure out a way to extract that out. Okay?
Is that just vacuuming a gas out of a plasma as it's happening?
I think one way to do it is probably magnetic field. There are clever ways out there, depending, because of different gyro motion or magnetic field. So deuterium and tritium. So you can selectively try to move it out. But that's a little sci-fi, to be honest with you. But I do feel like you need to figure that out, or you live with a neutron, the 14 MeV. And you say, listen, the wall loading of neutron is not as high. I found the material that can sustain this. It's not as much as DD, pure DD. Then I'll live with it. But then I'll change my vacuum vessel on a regular basis, or the first wall on a regular basis, and off you go. Then there's a lifetime to it. Okay, then that you can live with that. So, and I think that there might be companies that do that first, and then there'll be clever people like third generation say, listen, I don't want the tritium, and then people go work and and they come up with a pattern saying, I can remove the tritium and reduce the impact of the neutron. That's for D-helium-3.
Yeah.
Proton boron, similar, very similar. Proton, the boron is very heavy. So what you need is like, you're gonna have electron being heat and they'll radiate a lot. So right now from the curve that you see roughly, the fusion, the power you get from fusion is almost comparable to the radiation you get.
Yeah.
So you need to figure out a way to reduce the electron temperature so that the radiation doesn't occur. So that's another clever person, a group of people that will come up with a way to kind of preferentially heat the ion as opposed to heating the electron. Now, once you get there, you get 3 alpha particles coming in a proton. I think there it will be a lot more amenable to extracting this charged particle. People will be like, okay, we know how to do this. Accelerate. Charged particle is like an accelerator inverse, basically.
Yeah.
So you take the heat, instead of putting heat to accelerate, you basically, the thing that accelerated generate heat for you, electricity for you. So I would say there will be, but I feel for me the hardest is the helium-3. And then after PV11, and I think PV11 would be much down because you need 100 times more so about a billion degree compared to a DT temperature to fuse the PV11. So I don't know if I made it clear, but these are the challenge between helium-3, these advanced fuels.
Yeah. So like from the heating perspective, like obviously you have to get to high temperature, high density to be able to make some of this happen. Is it just a product of get as many neutral beams as I can, getting as much RF to hit some point source on this fuel to happen? Like what's the challenge of that? Why can't we get that hot?
You need to if neutral beam, you need to go much higher velocity. Right now for DT, you need to go about a 1 MeV, which is like 1 million electron volts. That's the speed at which you accelerate this neutral beam, this neutral particle. So I would say that, you need 10 times more roughly, which has not been. It's very challenging to do that. But we haven't looked at it. Someone could think about it and see carefully, do we need to do this? How do we get to these speeds, right? In terms of RF, that I'm not very knowledgeable about what it will take. I would assume that it's still power, so you need to make sure the coupling efficiency into the plasma is very good, because even if you have let's just say 60% coupling efficiency, 40 leak, out of 10, 100 megawatts, it becomes a lot that you dissipate. So you need to worry about that. Yeah.
So it's basically the enabling heating technology and some of the other enabling adjacent technologies need innovation to be able to make this happen.
Right. That's correct.
Okay. So when we think about translating these fuels into a power plant, is it more likely to be magnetically confined? Is it more likely to be an inertial concept, high compression concept? What architecture is required from a power plant to make it happen?
So that's an interesting question. I don't know much about it detailed, but from what I've looked at so far, I felt like you have more chance of getting to this advanced fuel with alternative concepts such as FRCs, as well as even laser ICF also. Yeah. For MFE is I don't know. I'm not convinced. I feel like it would take a lot more effort to do that and a lot more creativity from a physics point of view. But from an FRC point of view, I think that's where Tri-Alpha is looking at. Yeah. That's an interesting approach. Laser inertial confinement, that's also a possibility, just because they can put more laser and probably compress enough to be able to get to this temperature. I'm not sure what's the upper limit in temperature they can reach. So if they can get 10 times more, I think they have a chance at getting this advanced fuel to work in this concept. But I would say from the MFE point of view, I think there's probably a fundamental limit, just because the burn efficiency in MFE, you don't have this high density. The burn efficiency is much lower, at least for tritium, compared to, for example, ICF, where you burn most of your fuel because you compress, you have much higher density. So I think that's where you're gonna. That's why I think when I rank them, I feel like alternative concept, maybe ICF, and then maybe MFE.
So let's kind of move towards the application space. Sure. So if we're talking about, you spoke about potential compactness being a benefit of advanced fuels. What kind of markets or applications could open up from this?
So I would say that compactness, what people would be interested in would be to just go to set up a power plant at a naval base, or imagine you can have like in a submarine, right? That's one. Thrusters, right? You can have these proton boron 11 on the space station to provide power, right? Or for deep space travel, stuff like that. So I can see that. Or it could be something like a power plant that is modular enough that, you can create some microgrids, for a small area, small town. Come and plop it, you replace it, and you plop it again, you hook it up to the grid. So I would say this is where I see hospital. I can see these being like a good market for it. I know the military is interested in that a lot just because it's compact. They could put it on bases, so military bases. So I feel like those are places that could be interesting.
Right. So is your thinking when we're thinking about kind of the market penetration of this kind of fusion system, is it that, a DT system may potentially commercialize and this is a future generation thing? How do you see the timescales of advanced fuels compared to normal fuels?
So I do feel like DT will have to commercialize first. Okay. And what's going to happen, power plant, given the capital costs, need to live like 30 years, 40 years kind of thing, right? So, and then people will start realizing, listen, man, this thing breaks all the time. I got to change stuff. It's a mess, and then they might say, listen, let's find something. So I feel like the first 10 years of a DT power plant commercialized, maybe cost effective. I don't know. I feel like it might be as some sort of LCOE. When that runs, then the advanced fuel must start picking up a little bit more steam just because people realize the challenges of maintaining and then the neutron. Unless we find this magic material that self-heals, then you stick the material and then that's it. You don't have to change it. So this is where I feel like, so maybe 5 to 10 years after DTO comes online, we might start having people interested in that and pushing that.
Okay. Yeah, and do you think this new generation of plants potentially could be it would be the new paradigm of fusion energy? So, DT may be retired as an earlier iteration and this new thing comes and solves the problems?
So it's an interesting question you bring it up because I'm also interested in another aspect. I feel like DT will always be there, okay? We'll try to figure it out just because, like I said, it's like the energy per reaction is much higher. You get a lot more energy out of it. So you might have like a big city would have that in the background. Great. But what you might have now, and I feel like this is where it could be kind of sensitive, is like tritium is actually an export control fuel, right? So not everyone is going to have access to it. Yeah. So I can feel like, for example, the developing countries might be more amenable to have PV11, all this advanced concept, because there will be less like fuel supply challenges. And then they could because the grid system is not fully developed, they might have like microgrid in small town and then have small interconnect. And I do believe that's probably is going to be the next big market. But DT will stay around. And we have community in small town. You create your community with a small microgrid. You don't have to connect to the big grid. Yeah, that's what I feel like it would be the market for this advanced fuel.
Okay, that makes sense. And so looking at advanced fuels, what's some of the exciting research that's happening right now in this space?
I think advanced fuel. I think from my perspective, but I'm gonna be a little bit biased. One advanced fuel I didn't talk about: spin polarized fuel, right? Spin polarizing the deuterium, which actually enhances the cross section, so you can have like more fusion out of it. I think that to me that's exciting. Other for D-helium-3 or PPP11, I'm not so plugged into that, but D-helium-3, there are people thinking about how to extract the tritium out of it. Actually, PPP11, I'm aware of also another group that basically is trying to figure out how to preferentially heat the ion and not heat the electron. Those are purely theoretical right now, but exciting because I can see that there are like brain power invested in it to try to figure out. We know the challenges. Let's try to figure out from a fundamental physics point of view how to circumvent these challenges before we build a system. So it may take 10 years, right? Yeah. To get to understand this challenge and circumvent the challenge. But once they unlock that from on paper with a small test, then scaling to a fusion power plant, I think will be much smoother.
Okay. Yeah, interesting. You talked about the spin polarization. Can you spend just a couple minutes explaining exactly what that is?
So it turns out, this is something that actually was, there's a seminal paper from a scientist at Princeton back in the 80s. Turns out if you take the deuterium, it turns out have like a spin. Basically, it can spin around an axis, basically, this atom. And a nuclear spin, right? And then the tritium. When you bring them together, the contribution to fusion reaction is mostly due when the spin is a certain align or anti-align, right? So when align, what's good about it, you get 50% enhancement in cross-section, which actually for magnetic fusion translated almost close to 2x in fusion power output.
Yeah, wow.
And then it has like all the side benefit. For instance, instead of having most fuel, you need like 50-50 deuterium, right, for unpolarized. When you polarize, you may not need 50-50 to get the same power output that you get with it unpolarized. So you can get like 90-10, right? And then if you do 90-10, 90 deuterium, 10% tritium, what's good, you do not use up your tritium supply.
I see.
You breed much quickly. So this paper that Jason and I and Jacob just wrote and basically figured out this is really an interesting thing if we can do it. Yeah. And while it would take, it's a higher grade fuel. Think of your car, in a higher grade fuel. So it will be higher grade, but all the system, you can think the fusion power plant would be the same. You change the fuel, basically, you get more power output or not. You can choose to listen. I want to reduce the tritium content by a factor of 10 compared to a regular power plant. Sure, you get the same power output. A factor of 10, then you don't deplete the tritium supply. Or you say, listen, actually, I want to have a 2x in fusion power. Okay, you go 50-50 deuterium, but spin polarized, and you have a 2x. And then so it could be a mechanism to throttle the fusion power output on your grid. On a good day, basically.
Yeah, that's really cool.
So.
Yeah, amazing. So that's this emerging kind of field of research is people are working on. And
people are working in the past, we're just revisiting that, but more and holistically, including the whole fusion system. In the past, it was just looking at the nuclear physics point of view, was like cross-section enhancement. Yeah. But now you say, if you propagate that, what do we get?
So it's interesting you mentioned that, this is something people have been working on for a while. Someone in the 80s was looking at. I feel like that narrative happens a lot in fusion where someone goes, I picked this article off the shelf, dusted it off, and I'm building a fusion machine out of it or something like that. Yeah. Do you think there's like some of the answers to the questions that are just sitting in literature or in the body of science and knowledge that people have untapped?
So this is an excellent question because I've noticed that too. So here's what it is. In the 80s, we were barely close to get a fusion, right? We were like, that idea was floating. Oh, it's a great idea. Let's forget about it. And we're not there yet. Yeah. I think since we've hit like the NIF result, there's more enthusiasm to go back. Okay, now we are more or less sure we can get fusion. I mean, we do on paper, but it was not really experiment demonstrated. Yeah. So the confidence get built up. So then you go back and revisit, like, what am I missing? This idea that we saw in the past, was it completely crazy? Or was it like, okay, a little sci-fi because we're not close enough? Yeah. So I think it's worth revisiting. There's lots of old ideas that basically were like dismissed because tokamak, for example, was the leading contender at the moment. Now that we know we can get fusion, I think you're going to have a cohort of people looking at all the other concepts and figure out alternative ways to make them better and improve on them. And I think you're going to hear the story as we go for sure.
Yeah, amazing. So one of the last questions I'll ask on advanced fuels, we mentioned those three that people are exploring. Sure. Are there? We flirted a bit with sci-fi. Are there any fuel mixtures that are even further up in the periodic table that people could explore?
So helium-3 and helium-3 is something people can explore, but it's much higher temperature, and that's what the sun does. Yeah. So that's not an impossibility. That's something that you could do, but you got to figure out where you're going to get a helium-3. I do believe that there's not a lot left with enough cross-section. Sure. I mean, everything that exists, okay, you can do it, but the probability is not as great. And then so you're not going to get an energy return you want.
Okay. Yeah. That makes sense. So what excites you the most about fusion at the moment?
I think for me, I know that this is where we got to be. Yeah. And what excites me is all the enabling technology. I really think that we need to kind of just become more creative. Innovation we need to push innovation to be able to advance this. So I would say I've been excited after I heard the first time I heard the fusion, the NIF result. I was excited. I don't think I've been excited like this, but I felt like it was really good to see that, okay, we can do fusion. Even though people thought it was obvious, but to me, it was like a clear demonstration. And ever since now, I think what excites me is like, how do we make it easier? Finding clever ways to make it easier, because when it's challenging, I'm not too excited about it, but I want to make it easier. So that's pretty much what I like to do about fusion.
Yeah. Amazing. Well, it's really, really good to hear.
Thank you.
And it sounds like you've got a very important role at the intersection of, science, technology, commercialization with your work with the DOE. So I'm glad that there's people like you on the journey and even working on some of the next generation and iteration for fusion. So thank you for your time. Really
Thank you, Alex. Thanks for being a podcast. I appreciate it. This is good.
Yeah, great. And appreciate it. Thank you.
Thank you very much.